Hello, my name is Abdul Rahim Mustafa. My metric number is S72039. Today, I want to present about the chapter 2.2, thermistor temperature estimation. Okay, now I want to present about our project in chapter 2.2, which focus on thermistor temperature estimation using numerical method. A thermistor is a temperature-sensitive resistor that is widely used in temperature monitoring system because it is an inexpensive, highly sensitive, and respond quickly to temperature change. However, the relationship between the temperature and resistance is nonlinear. It's making it difficult to obtain and accept analytical solution. Therefore, numerical methods are required to estimate the root of the nonlinear equation Fs equal to e power of negative x minus x. In this project, we apply two numerical methods, namely the bicycle method and the regular fancy method, to determine the root of the equation accurately up to 4 decimal place and with an approximate error less than 0.05%. Next, I will explain the MATLAB code used in this analysis. The MATLAB program was developed to automate the interactive calculation for the both of method. Firstly, the equation Fs equal to e power of negative x minus x was defined together with the initial interval from 0 to 1. The program then repeatedly calculate the new root, estimate until the approximate relative error become less than 0.05%. For the bisection method, MATLAB calculate the midpoint of the interval in every interaction and check the sign of the function to determine the next interval. For the regular fancy, MATLAB use linear interpolation between the upper and lower bound to estimate the root more efficiently. The MATLAB result show the both of method coverage to approximate x equal to 0.5671, confirming the correctness of the program. Next, I will explain the hand calculation. For the hand calculation, we manually apply the formula for the both numerical method. In the bisection method, the midpoint of the interval was calculated using the average of the lower and upper limit. After evaluation, the function value, the interval was updated based on the sign change condition. For the regular fancy, we use the false position formula to estimate the root by drawing a straight line between 2 points on the function curve and finding its intersection with the x-axis. The interactive process was repeatedly until the approximate relative error satisfied the required tolerance. From the hand calculation, both of methods produce the root value close to 0.5671, which match the MATLAB result. This demonstrates that the calculation we performed correctly and that both methods are reliable for solving nonlinear equation.
Assalamualaikum. My name is Siti Numaisara binti Badiu Zaman. My metric number is S72940. Now I want to present chapter 3.3, which is signal attenuation in underwater communication. And this one is a question of signal attenuation in underwater wireless communication. I want to explain two questions in this topic, which is estimate the intensity I at x 0.75 meter using third order Newton divided difference method and third order Lagrange method. And the second one is estimate the intensity at 0.75 meter using both method and compare the result. In introduction, this experiment analyzed a high-speed underwater optical wireless communication link between a sea floor sensor and surface buoy. The optical intensity reading at 0.75 meter was missing due to laser misalignment. To estimate the missing value, two third-order interpolation method, Newton divided difference and Lagrange were applied and compared using MATLAB and manual calculation. This one is objective, which is to apply the third order Newton divided difference method and to solve the interpolation problem using the third order Lagrange, and lastly to compare the numerical finding and ensure MATLAB. Based on the experimental data obtained for the underwater optical wireless communication link, both the third order Newton divided difference and Lagrange interpolation method were able to estimate the missing signal intensity at a transmission distance of 0.75 meter. The Newton method produced a value of 3.9235 millivolt, while the Lagrange method gives 3.9236 millivolt. The difference between the two results is very small, which is 0.0001 millivolt, indicating the both method provide highly accurate the consistent estimation. This variation is mainly due to rounding during the manual calculation process. Next, when simulated in MATLAB, both the Newton and Lagrange interpolation method produce the same result, confirming that they are mathematically equivalent. However, the Newton method is more flexible because new data points can be added without recalculating all confidence. In contrast, the Lagrange method requires the entire calculation to be repeated when the dataset changes. The interpolated value at 0.75 meter is reasonable as the signal intensity decreases with distance due to absorption and scattering in water. Moreover, the missing data point was successfully estimated and the experimental curve was completely accurately.
Hello, my name is Chingo Kwan S70483, and now I will present the chapter 5.1 RC charging circuit. Okay, let's look at the problem of this question. We are given the first order differential equation that govern the behavior of an RC charging circuit, 12 equal to 0.04 dVdt plus 0.08 V, with the initial condition V0 equal to 0 and a step size of H equal to 0.2. Our objective is to determine the capacitor voltage at T equal to 0.6 using two numerical methods, Euler methods and Hughes method. For validation purpose, the numerical result will be compared against the asset analytic solution Vt equal to 150 times 1 minus exponential negative 2t. This comparison allows us to evaluate the accuracy and reliability of each numerical method in predicting the transit response of the RC circuit. Okay, here we have our manual hand calculation. For Euler method, we use the standard iterative formula using the initial slope of each interval at a step type of 0.2. We calculate step by step up to t equal to 0.6 seconds, arriving at an estimated capacitor voltage of 114.6 volt. Okay, next we calculate the SS solution at t equal to 0.6, which gives us 104.8209 volt. Comparing our approximation, the Euler method shows a true percentage error of 12.90%. In contrast, the Hughes method is a much closer approximation of 102.8352 volt with a true error of just 1.89%. Okay, to verify our mathematical steps, we implement the algorithm in MATLAB as seen in the command window output on the right. The script successfully executes both iterative loops. The automated simulation perfectly matches our hand calculation, confirming an error of roughly 12.90% for Euler and 1.89% for Hughes. Okay, in conclusion, while the Euler method is simpler and uses linear calculation, its global truncation errors is proportional to h. The Hughes method utilizes a quadratic slope averaging approach, giving it a global truncation error proportional to h squared. This made the Hughes method significantly more accurate and faster at converging to the true analytical value for the same step size. That's for me. Thank you.
Chapter 6.1 Electronic Test Calculation. For introduction, focus on numerical integration using the trapezoidal rule and rhomboid integration methods. These methods are used to estimate the value of a definite integral when an exact and analytical solution is difficult to obtain. The trapezoidal rule approximates the area under a curve using trapezoid, while rhomboid integration improves accuracy by applying Richardson extrapolation to successive trapezoidal approximates. For objective, 1. To evaluate the defined integral using the trapezoidal rule with n equal 1, 2, and 4 segment. 2. To compute the integral using rhomboid integration. 3. To determine the percentage through error of each numerical approximation. And last, to compare the accuracy of the trapezoidal rule and rhomboid integration. Methodology and calculation. The methodology used in this study involved evaluating the integral 0 to 3 square 1 plus d2 dt using numerical integration techniques. First, the trapezoidal rule is applied with n equal 1, 2, and 4 segment to obtain approximate value of the integral by dividing the interval 0, 3 into equals subinterval and calculating the area under the curve. The result obtained from the trapezoidal rule are then used in rhomboid integration, which improve the accuracy of approximation through Richardson interpolation. Finally, the accuracy of approximation are assessed by calculating the percentage true error using the given true value of 5.653. All calculations are performed using 4 decimal places are required. Okay, next, MATLAB calculation. For first image is calculation MATLAB, and the second image is result for this calculation MATLAB. Next is handwriting. Based on the calculation, the integral 0 to 3 square 1 plus t2 dt was first evaluated using the trapezoidal rule with n 1, 2, and 4 segment. The approximate values obtained were 6.2435, 5.829, and 5.6971 respectively. As the number of segments increased, the approximation became closer to the true value, showing an improvement in accuracy. This trapezoidal result were then used in rhomboid integration, where successive interpolation produced value of 5.6867, 5.6542, and a final rhomboid estimate of 5.6520. Comparing this result with the given true value of 5.653, the percentage true errors for the trapezoidal were 10.45%, 3.06%, and 0.78% for N1, N2, and 4 respectively. The final number result gave the smallest error of only 0.03%, demonstrating that rhomboid integration provides a much more accurate approximation than the basic trapezoidal rules. Okay, next, discussion and conclusion. Based on the result obtained, the trapezoidal rule produces an approximate value of 6.2435, 5.8259, and 5.6901 for N1, 2, and 4 respectively. As the number of segments increase, the approximation becomes closer to the true value of 5.653, indicating that the accuracy improved the final subdivision subdi- subdivisions of the interval. The representative true error also decreased from 10.45% to 3.06%, and finally 0.78%, showing that increasing the number of the segment reduced truncation error. Furthermore, when rubber integration was applied, the presented true error of only 0.03%. They demonstrate, uh, they demonstrate that rhomboid integration is more accurate because it uses Richardson interpolation to reduce numerical error and accelerate convergence toward the true value. Okay, for the conclusion, in conclusion, both the trapezoidal and rhomboid integration were successfully used to evaluate the given integral. The result showed the increasing the number of segments in the trapezoidal rule improve the accuracy of the approximation and reduce the percentage true error. However, rhomboid integration provide the most accurate result with an approximate value of 5.6520 and the smaller error of 0.03%. Therefore, robot interrogation can be considered the preferred numerical method for this problem because it achieves higher accuracy without requiring a large increase in the number of subinterval. Thank you.